A diode, or equivalently a PN junction, consists of a p-type doped semiconductor joined with an n-type doped semiconductor, both of which we have examined in detail. The circuit symbol adopted for the diode is a triangle with a line at its end. According to this symbol, the line segment represents the cathode or negative terminal, while the triangular portion represents the anode or positive terminal. Since we have already examined the behavior of the PN junction, the diode exhibits several distinct operation regions. The current voltage characteristic in the primary region of operation is given by the relation IAD equals I sub s times a raised to the power of V sub d divided by eta times V sub t minus 1. In this relation, I sub s is the reverse saturation current which arises when the diode is reverse biased and is generated by minority carriers. Its magnitude is extremely small. V sub t is the thermal voltage defined as K times T divided by Q, where Boltzmann's constant T is the absolute temperature in Kelvin and Q is the electronic charge. At room temperature, V sub T typically lies between 25 and 26 millivolts, and for simplicity in calculations, a value of 25 millivolts is generally adopted. The quantity eta depends on whether the diode is fabricated as part of an integrated circuit or as a discrete device. For integrated diode, eta is typically taken as 1, whereas for discrete diodes, it is typically taken as 2. Now, if we wish to examine the current voltage characteristics of the diode under forward bias, we may consider a circuit in which a DC battery V places the diode in forward bias, allowing a result current to flow through it. We therefore wish to plot I sub D in milliamps as a function of the diode voltage. As noted, in this case, below a certain threshold voltage denoted V sub gamma, the current remains approximately zero in the forward bias region. Beyond this threshold, the current increases exponentially. This value of V sub gamma differs between silicon and germanium diodes. For silicon diodes, it is approximately 0.7 volts, shown here in red on the curve, while for germanium diodes, it is approximately 0.2 or 0.3 volts. In practice, V sub gamma values in the range of 0.6 volts are also common, though 0.7 volts is typically used in calculations to ensure the current has clearly entered the exponential region. For silicon diode, I mean. Otherwise, actual values may range from 0.65 volts for silicon or even 0.16 volts for germanium in some cases. Under reverse bias, however, the IV curve behaves differently. Over a very small region, the current rises from 0 toward a value denoted I sub s. following a curved profile, and then remains approximately constant at I sub S over a substantial range of reverse bias voltages. I sub S in silicon diodes is typically smaller than that in germanium diodes, though both are generally on the order of microamps, provided the reverse voltage does not approach the breakdown voltage. Okay, let us now consider an example. In the circuit shown below, the reverse saturation of diode D1 and D2 are given as 1 nanoamperes and 10 nanoamperes respectively. For what value of the input voltage V will the current I2 become twice the current I1? Let us examine the circuit diagram. The two diodes are connected in anti-parallel, meaning D1 and D2 are oriented in opposite directions relative to each other. Consequently, the voltage V places diode D1 in forward bias and diode D2 in reverse bias. We wish to find the value of V for which the current I2, that is, the current through the diode operating in reverse bias, becomes twice the current I1. If we take D1 to be forward biased, we may approximately write I1 as I sub S1 times raised to the power of V sub D divided by eta times V sub T, neglecting the minus 1 term related to the dominant exponential term as an approximation. Diode D2, being reverse biased, carries a current approximately equal to its reverse saturation current, I sub S2. Assuming V sub D has reached a value at which the current has settled to I sub S in the reverse bias region. The problem states that I sub 2 must equal twice I sub 1. Therefore, I sub S2 equals twice I sub S1 times raised to the power of V divided by 2 times V sub T, where eta is taken as 2 since the diodes are treated as discrete devices. Taking the natural logarithm of both sides, we have this relation V sub in equals to 2 times V sub T times natural logarithm of 5. I sub S1 equals 1 nanoamperes and I sub S2 equals 10 nanoamperes in this equation. So we have this answer corresponding to answer choice number 4. We now turn to the reverse breakdown voltage of the diode. In the conduction region, once the voltage exceeds V sub gamma, the current must transition to its exponential form prior to this threshold again. The current remains approximately 0 and V sub gamma as noted represents the threshold conduction voltage. As discussed, regarding the breakdown region of the characteristic curve, the current initially rises from 0 to a value of I sub S and then remains approximately constant at I sub S over a range of reverse bias voltages. However, beyond a certain point, this behavior no longer holds. In the reverse bias region, as previously discussed, the current rises from 0 to I sub S and then at a certain voltage known as the breakdown voltage, a reverse breakdown voltage, typically expressed as a positive value, although it corresponds to a negative diode voltage, the current profile changes dramatically. For instance, breakdown voltages are commonly cited as 50 volts, 100 volts, or 200 volts, of all of which correspond to the negative voltage region. At this voltage, due to avalanche and Zener breakdown phenomena, a substantial current can flow in the reverse breakdown condition, and the slope of the current curve increases sharply at this point. We now investigate the resistance of the diode. The resistance of a diode can be defined in two distinct ways, corresponding to two operating regimes. A resistance in the DC or static regime, denoted R sub capital S, and a resistance in the AC or dynamic regime, that is the static resistance and the dynamic resistance. Let us begin with the static resistance. If the diode is operating in the conduction region under forward bias and we are situated at an operating point Q, where V sub D equals V sub dq and I sub D equals I sub dq, then the ratio of V sub dq to I sub dq at this point is precisely the static resistance of the diode. The dynamic or AC resistance is defined differently. At the operation point, we compute the slope of the curve, specifically delta V sub D divided by delta I sub D. Since I sub D is typically expressed as a function of V sub D, we may equivalently compute delta I sub D divided by delta V sub D and then invert it. Thus, the dynamic resistance is defined as delta V sub D over delta I sub D, which is the derivative of V with respect to I. Since I is typically treated as the independent variable and V as the dependent variable in this context, we may instead compute the derivative of I with respect to V and raise it to the power of -1. We compute the derivative of I sub D with respect to V sub D and then invert it. This yields this fraction. The denominator equals to I sub dq plus I sub s, and since I sub s can generally be neglected relative to I sub dq, as I sub dq is typically much larger than I sub s, the dynamic resistance simplifies to approximately eta V sub t divided by I sub dq. Therefore, once the DC operation point is known, both the dynamic resistance and the static resistance of the diode can be readily calculated. Okay, consider a simple example. In the circuit shown below, the rated voltage and current of the silicon diode are 0.7 volts and 10 milliamperes respectively. A. What value of the resistance R is required for the diode to operate at this voltage and current? B. Calculate the static and dynamic resistances of the diode at the rated voltage and current and at a temperature of 300 degrees of Kelvin. Let's solve. A. With a KVL, we have the unknown R must equals 4 minus V sub D divided by I sub D, and we obtain the unknown R equals to 0.33 kilo ohm. This is A, and for B R sub S equals to V sub D divided by I sub D, that is 0.7 divided by 10 equals to 0.07 kilo ohm or 70 ohm. And for dynamic resistance, R sub D equals to eta times V sub T divided by I D, and it can be obtained from this equation equals to 5.2 ohm.